ATP powers cellular work. In this concept, we will be discussing how ATP, a nucleotide, powers cellular work. The functioning of ATP in cells explains how these shaggy Clydesdale horses survive cold winter days. We will be discussing the structure of ATP, how hydrolysis of some of the covalent bonds in ATP releases energy, how ATP functions in the cell, and how ATP is regenerated so it can power more cellular work. ATP is a nucleotide with 3 phosphate groups. See, here's the pentose sugar. In this case, it's a ribose. Here's the base adenine, and here are those 3 phosphate groups. The covalent bonds between the phosphate groups contain a lot of potential energy. When those bonds are broken during the removal of the end phosphate group, energy is released. The energy that is not lost as unusable heat can be used to power reactions that require energy, or endergonic anabolic reactions. The reaction that breaks off the end phosphate from ATP is called a hydrolysis reaction. The resulting products of the reaction are energy, inorganic phosphate, represented by the P in the circle with the I, and ADP. ADP stands for adenosine diphosphate, or 2-phosphate. This process of releasing energy and the conversion of ATP to ADP is a catabolic reaction, and it powers anabolic reactions. The reverse is true. The cell uses catabolic reactions to regenerate ATP from ADP, which is an anabolic reaction. And around we go. So, you may ask, why doesn't the cell couple catabolic pathways to anabolic pathways directly? Why use ATP as the go-between? It is for the same reason that most societies use money, a symbol of a valuable object, instead of using barter of actual objects or services. Say we live in a society that uses a barter system instead of money, and I want to buy eggs from the store. I have a book that I know the grocer wants, so I take the book and walk down to the store. I tell the grocer that I have the book that she wanted, and in exchange for the book, I would like some eggs and some ham, since I'm in a haggling mood. The grocer tells me she got that particular book from another customer, but she wouldn't say no to the sequel. I walk over to the bookstore to try to exchange the book I have for the sequel the grocer wants. The bookseller says he has too many of that particular book, but he needs someone to balance his accounts for him. Since I'm pretty good at math, I'll say I'll do it for the book the grocer wants so I can get my eggs and maybe some ham. His accounts are a mess, so it takes me all day. I stagger off toward the grocer's, both books clutched to my chest, hoping somebody else hasn't used the sequel to barter for my eggs and ham. Now let's do the same scenario with money. I want some eggs from the local grocery store. I take money, which is a symbol of the service I've performed in teaching this class, and I walk down to the grocery store. I see the price for the eggs is less than the amount of money I have in my pocket, so I pick up some ham too. I walk over to the register, where the grocer is filling in for one of her checkers, and give her the money. She gives me the eggs and ham. The grocer then goes to the bookseller and uses the money I gave her, which is a symbol of the eggs and ham, and gives it to the bookseller in exchange for the book she wants. See how much easier using money is? It's the same way for the cell. ATP can be used to power any anabolic reaction, and any catabolic reaction can be reused to regenerate ATP. Whereas some anabolic reactions may not play well with some catabolic reactions. Let's look at a specific example of how ATP can use to power an anabolic reaction, that of combining glutamic acid and ammonia to make an amino acid, glutamine. First, we use the energy from the hydrolysis of ATP, an exergonic reaction, to raise the potential energy of glutamic acid. Transferring a phosphate group from ATP to glutamic acid transfers energy. Energy goes with the phosphate group. Then we break the bond between the glutamic acid and the phosphate group, releasing more energy. The cell uses this energy to put the ammonia on the glutamic acid in place of the phosphate group, forming the glutamine. The phosphate group can be placed back on ADP, but it will take energy from an exergonic reaction to do so. Here is an example of how ATP can be used to power the movement of solutes from an area of lower concentration inside the cell to an area of higher concentration outside the cell. Remember, with diffusion, the solute wants to go away the other way to achieve equilibrium. Here is an example of ATP being used to power a motor protein that moves a vesicle along a cytoskeletal track to get the vesicle where it needs to be. Without the motor protein, the vesicle would just randomly bump along in the cell. Maybe it would reach where it needs to be in time, maybe it won't. This way, using ATP as money paid to the truck driver, so to speak, the vesicle gets where it needs to go in a timely manner. So, to summarize, ATP undergoes hydrolysis to provide usable energy for an anabolic reaction. Other catabolic reactions are used to provide energy to regenerate ATP from ADP and inorganic phosphate. Hopefully this concept was easier than the last. In any case, keep pushing through and watch all the concept videos at least once. Then go back and rewatch the ones that you still have questions about. Read those sections in the book more thoroughly.